mic. All right, welcome back to operating systems. So this fun lecture hall has a penalty box in the middle, so if you're too loud, I guess you can go in that. I don't know why that's there. All right, anyways, kernels. So let's continue our journey on operating systems. So where we left off, and this time I have unmuted my mic, so recording should be okay. So we were left off with this program that I told you was a program. We looked at the first 4 bytes. We saw it was 7F ELF, and I said, that's the file format for executable files. So let's go ahead and, again, we'll just make sure it works as a little sanity check, and prints hello world whenever I execute it. And if I look at it, hello world, links, I can see its size is right here at 168 bytes, so pretty small, and that's hello world. So here's an aside before we get into it. So there's basically 3 major ISAs today. In your computer organization course, you use ARM, and ISA stands for instruction set architecture. We won't have to go into details, but it's a good thing to know since you are all you're all in ECE. So there's x86 64-bit, which is most of your desktops and non-Mac laptops. And servers, everything will probably be that architecture. Then there's ARch64, which might be called ARM64. Those are the newer MacBooks. Those are your phones. And close to what you had in the computer organization course, that fun ARM processor. And then there's RISC-V, which is like an open source implementation similar to ARM. So an operating system we're going to start looking at throughout this course is written in RISC-V, which is pretty easy to understand, and we'll just use that as a basis. But again, like I said in the previous lecture, you don't really need to understand assembly or how to write assembly. Just we'll read a little bit of it, and I'll be there to help guide you through it. So we'll just touch on all of them a little bit because sometimes it will matter. Most of the time, it won't matter. So going on abstractions, just to explain what we had with opening files and stuff. So our next abstraction after a process is a file descriptor. So because our processes are all independent, the next most obvious question you might have is, well, if they're all independent, how do they do anything? How do they talk to each other? Like, how do you transfer data between processes if they're all independent? Well, there's a thing called IPC, and that stands for inter-process communication, just a fancy way of saying I want to send data between 2 different processes. So instead of being independent, you don't want it to be completely independent because you need some data to go back and forth. So a file descriptor is a resource that users may either read bytes from or write bytes to, and all it is a number, which is an index, and that is unique to a process. So if in the other example we saw before, we opened a file, that would be represented as a file descriptor with some number, let's say index 3. So throughout that whole process's life, you just open 3, file descriptor 3 is valid until you eventually close it. But nothing else can monkey with your file descriptors. They're one of the other independent things between a process, but you can use a read and write to send bytes to and from that file descriptor. So file descriptor, it's only called that. It doesn't necessarily represent a file, just things that kind of look like files, which is why it's an abstraction. So it could actually represent a real file, but it doesn't have to. And it can represent something like your terminal. So your terminal is something that you can write bytes to and read bytes from because at least in first year, you probably wrote an application where you can type something, press enter, and then process that data and then print something at the end. So you're reading and writing bytes when you're doing that. All right, system calls. So system calls are how you make requests to the operating system. And at the beginning, we can just represent them like C functions. Behaviorally, they're really not much different. They only really differ in their implementation. So here's 2 system calls we actually need for a basic Hello World program. the first one is called write, and it takes 3 arguments, and all it does is write bytes from a byte array specified by that buff and how many bytes to write specified by count to that file descriptor specified by FD. So FD is the file descriptor I want to write bytes to. Buff is an address that represents the start of a byte array that just has to be initialized, and that's where the operating system will write bytes to starting from. And count is how many bytes maximum you want to write. And then the other system call, oh, yep.
What's the difference between the type size T and S size T?
Oh, okay, yeah, so there's a question, what's the difference between size T and S size T? S size T is signed size, so it can be negative. The other one is unsigned, so it can't be negative. And the reason this, so write returns the number of bytes written, and it will return a negative number if there's an error. So that's why it's signed. All right, the second system call is called exit group, and that exits the current process and sets an exit code corresponding to that status. So status is an integer here, but the operating system only cares about the least significant byte, so you can only actually return error codes between 0 and 255. And you can specify like 1,000,000 if you want, that fits in an int, but it's just going to chop off some of it. The only thing it cares about is 0 to 155. Yep.
So do file descriptors have like a maximum size or something? Like what happens if I put like 2 billion in the count?
So file descriptors just represent a file, and then if you try to write 2 billion to it, the operating system would be like, no, I can write the first few thousand, and then it'll return it wrote the first few thousand. And then if you want to write 1,000,000, well, then you have to call it again and go over and over again. Or it could just say, you're not allowed to do that anymore if you go too far. Okay, so these 2 system calls are actually all we need for hello world, and they make requests directly to the operating system. So before we get into this, we need to know a bit more about file descriptors and magical file descriptors. So nothing is enforced by the operating system. This is just a convention, but everybody follows this convention, and that is how all your terminal applications actually work. So by convention, whenever you start a process, there should be 3 open file descriptors, and they have specified numbers. So file descriptor 0 is always standard input. It's just 0 standard input. That means you should be able to read bytes from that file descriptor. Then you have file descriptor 1, which is standard output, or write. So that's where you write bytes to, and that means usually that represents your terminal. So if you say print, it goes to that file descriptor. If you have used C++, cout, it's file descriptor 1. If you've used C and use printf, that's file descriptor 1. If you use literally any language, it's standard out just means file descriptor 1. And then there's file descriptor 2, which some of you may not have used, which is standard error, and it's just meant for you to write error codes to. Sometimes people don't do that. Sometimes people do that. Generally, you want to write errors to that, but some people don't do it. So if we were to kind of write a iffy hello world program in C, it would look something like this. It would just be a function that doesn't return anything and doesn't take any arguments, because we don't need that for hello world. We don't use any of the arguments, and we don't need a main because we're trying to do the least amount of things possible. So just naming something main doesn't matter. I could have named this whatever, but I don't really need any arguments. I'm not going to return anything because I'm going to write to file descriptor 1. I'm going to write hello world, so that'll be represented as an array of characters, or char star, so point to the first character in hello world, and then I'll say I want to write 12 bytes. So that should represent, so hello, that's 5, space 1, world, it's another 5, and then \n is the new line character, which is just something you should probably do. So that's another byte. So in total, we want 12 bytes to 1, which is standard output. And then if we're done with our program, we just call exit group and just say 0. 0 by convention means nothing went wrong. We have no errors. Yeah.
So you don't need a main function for this?
Nope. Yeah, the question is, do I need a main function for this? And the answer is no. If I'm writing like the most basic hello world thing, main, before, we won't see it, but before main executes, a bunch of stuff happens. And we'll explore that in a bit too. But we don't, if we're writing the smallest thing possible, we don't need a main. If we could magically tell the operating system to just start executing this instead of main, we don't need it. Yep.
So what happens if you like omitted the exit group 0 line?
Yeah, so that's a good question. What happens if I just omit exit group 0? So if I omit exit group 0, well, this will get compiled into some instructions, and they'll have to get mapped into memory at some point. So right after the write, if I omit exit group, it would just be invalid memory. It would try and execute that, and then it would just fail. So it would just die, it would crash, the operating system would have to do something with it. But it would, yeah, so it would probably die, but it would die an untimely death and a messy death. So this is a proper hello world that actually exits. Yeah.
Sorry, but just to clarify, for a file descriptor is an abstraction for either a file or a terminal, right?
Yeah, for now it could represent a file or a terminal.
Okay, and if it was, what would happen if you change 1 to 2?
Yeah, so in this case, if I change 1 to 2, by convention, I would be writing to this file descriptor, standard error.
Yeah.
So by default, your terminal shows both of those. So it would look exactly the same if I change the 1 or
Oh, it
1
would be an
to
error
2.
message, but the error message would say hello world.
No, so it would look the same. The only difference is just what file descriptor it wrote to. So eventually when we know how to manipulate file descriptors, if you only care about errors, you can just see everything from file descriptor 2. If you don't care about errors, you can ignore file descriptor 2. We'll see a bit of that in a sec. Yeah.
So what's the difference between exit group 0 and then like return 0 in like a main function?
Yeah, so the question is, what's the difference between exit group 0 and just returning from main? So exit group 0 is what will actually happen on like Unix operating systems. That's the request you have to make to the operating system. So the only difference between returning from main in C will take care of figuring out how to exit a process on whatever operating system you're running on. So returning from main on Linux will eventually call exit group with whatever number you return from main. So you know specifically what it does on Linux. But yeah, but on Windows it'll do something different because that won't exist. Right, so C does some little nice things for us. We thought it was low level, but it actually does some things. All right, any other questions with that? This is a whole new world, right? All right, so we have to take another quick aside too, a difference between an API and an ABI. You might not have heard the term ABI before. Hopefully you heard the term API before. So API, Application Programming Interface, it's meant to just abstract the detail and describe arguments and return values and generally what the function does. So like a function takes 2 integer arguments and returns you an integer that represents like the addition between them or something like that. So that would be like an API description. An ABI description is like low-level details that you may have monkeyed around with in computer organization, how to set up, you know, like prologue to function calls and all that stuff. That's all specified in something called an ABI, and that's like explicitly how to pass arguments. So if you're in C, we pass arguments on the stack. In your computer organization course, you probably picked certain registers to represent certain things. But that would be defined in something called an ABI. And in C, the C calling convention, yeah, it does just pass arguments on the stack instead of explicitly using registers. Okay, so with that, here is the system call ABI for Linux, specifically on ARM64 or AR64, whatever you want to call it. So because the operating system is running something else. It's not in C. You can't just make C function calls to it. That doesn't make any sense. So there's no functions to call because there's no addresses, because the kernel won't just give you its memory, let you access its functions or anything like that. So you can't just call a function if you want to make a request to the operating system. You have to do something called a system call. And a system call, you did interrupts in computer organization. So how we make a function call to the operating system is there's a special instruction that we're allowed to execute that will generate an interrupt to the operating system. So specifically for ARM64, it's called the SVC instruction. I forget what it stands for, like supervisor vector something call. I forget exactly what it stands for, but it stands for something. Basically, all that instruction does is generate an interrupt. And then the convention is to pass arguments in registers. So register X8 should just have a number that represents what function call you want to make. So for example, write would be function call some number. Exit group would be another number that's supposed to represent, hey, I want to make an exit group function call. And then it takes 6 arguments passed in registers X0 to X6. So anyone think of any limitations to this interface? Yep. Yeah, if I have more than 6 arguments, I'm screwed now, right? In C, are you allowed to have more than 6 arguments? Yep, because you can just, it's on a stack, so you can just keep popping or keep pushing as many arguments as you want until you run out of stack space, of course, but it's essentially fairly unlimited. All right, any other ideas or limitations this has? Yep.
What if you call a function in a function?
So in this, you can't make recursive function calls or anything like that. So you just make one request to the operating system, say, do this for me, please. So the operating system could implement that in a recursive way, but you can't make recursive calls or anything. Yep.
So is this like calling convention shared between multiple different architectures? Like it goes through register 0 to register 5 for arguments?
So this is specifically for ARM64 using Linux. So every operating system and architecture is going to have its own calling convention.
So you wouldn't be able to like reuse code for syscalls between different operating systems. You just like copy and paste it.
Yeah, the question is, oh, can I just reuse system calls to operating system? The answer to that is no. So they'll be all slightly different. So that's one of the reasons why someone came up with the C standard library. So you don't have to worry about this. You just let it figure out what system call it actually needs to make for your system. So that's like one of the things the standard C library does. Yep.
What are registers 6 and 7 being used for? Or are they just?
Oh, yeah. So registers 6 and 7, there'll be like caller saved or callee saved. Well, I'm just kind of ignoring it just because we won't have to write this. It's only for showing you. So yeah, we don't have to care about the calling convention. So many things will just do this for you. Okay, so yeah, like I said before, programs on Linux and I guess PlayStation stuff use the ELF file format. So it stands for Executable and Linkable Format. ELF, nothing to do with me. And it's the format for both executables and libraries, and we'll see libraries in the next lecture. So they always start with the same 4 magic bytes. That's 7F and then ELF in ASCII. They're called magic. They're literally called magic. That's like the whole magic of a computer. It's just random numbers that mean something if you know what the random numbers are supposed to be. So this is like a very common thing. So there's a Wikipedia link for file signatures. So by reading the first few bytes of most file formats, you can figure out what it is. So like PDF files start with ampersand PDF and then a dash. That's how every single PDF file in the world starts. So that's the file format. So our bytes represent an ELF file. We already know that because we looked at the first 4 bytes and it matches. So the whole thing, so we'll break it up into parts, but basically that whole ELF file just says load this entire executable file into memory at address 10,000 hex. And the header file, if you look at the specification for ELF, which is a fairly boring document, it says, well, the header file has to be 64 bytes. So it's 64 bytes. Basically, it just gives you some information about the executable so that the operating system can tell. One of the bits of information in it is like the ISA. So the operating system can tell what ISA it's running and what the file is. And if they don't match, it can say, I can't execute this without trying any further. Things like that. After the header file, there's a program header, which basically just, that's the part that says where to load it into memory. And it's 56 bytes of information. So 120 bytes of our 168 byte file is literally just filling in information for this file format, which is fairly boring. So we have 48 bytes left. There are 36 bytes for instructions, and we'll disassemble them and see what they are. And then the last 12 bytes are for the actual string hello world. And in this case, if you calculate the difference from the start of the file to where the instructions start and where the data starts and convert it to hex, well, instructions would start at byte 150 or 120 because the first 120 bytes are the header and the program header. So instructions, if we loaded it at address 10,000 hex, well, instructions would start 120 bytes after 10,000 hex. So if you convert 120 to hex, it is 78, and if you add them together, you get that address. So instructions would start at that address, and if you do the same thing, and you just know that the string starts after the instructions, and that was our choice to make, it would start at byte 156, which is 9C in hex. Again, add it together. So the string would start at that address. And there's a command you can use, read elf-a. It will give you all the gory details of the file format if you're really curious. I don't super recommend it, but hey, I can't tell you what to do. I guess I kind of can, but whatever. All right. So this is visually how the ELF file gets divided. So that file header was 60 bytes. Everything that's in it, so it also has a field for like what endianness this file represents, the instruction set architecture, the ABI it's expecting to use, so in this case it's Linux, the entry point. So in that header file, the entry point means where to start execution if I want to start executing this process. So in this case, if I want to start executing my beginning of the instructions, I should set my entry point to address 10,078. And that's where the operating system knows where to start executing your program. It's in that header file. And then in this cyan color, there's a program header, and that says what to load into memory and where. So in this case, all those bytes basically just say load this entire file at address 10,000 hex, and that's all it says. So pretty verbose for saying that. And then the next bit is the actual instructions. If we just take the assembly and just convert it to machine code, that's what they are. And then at the end is our string itself. So this is what the instructions look like if you throw them into a disassembler for ARM. So it follows that calling convention I showed you earlier. So X8 is our system call number. In this case, let's just say in a decimal. So that's what system call to make, and we want to make a write system call first. So there's a whole table you can look up. So the write system call means I want to call function 64. So 64 represents write. The first argument was the file descriptor. So if we want to write hello world, we should probably just write it to standard out. So that would be file descriptor 1. The next argument is the address of the string. And because it's ARM, we have to build it in two parts. So we have to build the lower byte, and then we have to build the upper bytes. So 9C was the lower part of the address. And then if we do this move K instruction, We will add 10,000 to it to give us our 10,009C, which is the beginning of our string. Then the next argument is, and again, if you can't read this, it's fine. This is like the only time we'll read ARM assembly. This is just to illustrate how you actually make system calls. So the last argument is the number of bytes, and we want to write 12 bytes. And then to start a system call, after we set up all the registers, we execute this SVC instruction, and that will generate an interrupt, and then the operating system gets to handle it. And some of you have handled interrupt before, so you can use your imagination with what it kind of looks like to the operating system. Now, after that system call is done, it will just continue execution. So the next time so after it's done right, it will come execute this instruction. We want to do an exit group system call. It's number 94. It only takes one argument, 0, and then we do SVC, and that does the exit group system call, and exit group never returns because our process is now dead. It's exited, it's gone, no more. Yep.
So just to be clear, this is just one example of using SVC specifically for ARM on Linux to generate a system call.
Yeah, this is specifically how to do system calls on Linux using ARM64. Yeah, so if you want to do this on x86 on Linux, the register names are obviously going to be different because they don't exist, right? But it's pretty much similar, just the register names are different. If you want, FreeBSD is the same, Mac OS is pretty much the same. Windows is a bit weirder. But this is basically how you do it and how it will always work no matter what operating system, just the details are going to change. So that string, 12 bytes, that was hello world, and we just ASCII encoded it. So a fun low-level ASCII tip that might not be so fun to some of you is it was designed in such a way to know if a character is lowercase or uppercase by looking at a single bit. So bit 5, if bit 5 is 0, it means it's uppercase, and if it's 1, it means it's a lowercase, and which just means the values differ by 32. So if you ever, for some reason, need to do low-level ASCII stuff, then that's a good thing to know. Hopefully, you never need to know that fact. I don't know why I put it in there. Anyways, so that's every byte. So every byte is useful. And let's go ahead and see what C does. So that was, again, 128 bytes. And yeah, before I even show that, can you already spot the difference between strings compared to C? Oh, no, that wasn't a hand. So what do C strings always end with? Yeah. A null character. Did I have a null character there? So this was my string. Not null, not null, not null, not null. Go through that. Null is just another word for 0. So none of those is 0. As an aside, if it had to be a C string and it said, oh, okay, write until a 0, well, then suddenly my write system call is useless. I can't write zeros to anything. And if you couldn't write 0 to a file, that'd probably be pretty bad. So ending a string in 0 is literally just a C convention. The operating system doesn't care. It's not a thing to the operating system. So whenever you see, it will just ignore that null character. That just means the string's done and don't process it. Yeah?
A trivial question. Could you go to the previous slide?
This?
Oh, you said ISA AVI entry point. What do you mean by entry point?
So entry point is the address to start executing instructions. So in this case, our entry point, if we say we want to load things at 10,000, our instructions would start here at this address. So this would be our entry point. So if you do that read elf on the file, it will say that address as the entry point. That just means I want to start executing at the start of my instructions. So if I change that, it would skip some instructions and then bad things would happen. Okay, let's see what C does. Yep.
What if you change that number to like a previous number that's lower or a number that's higher?
Which number?
That entry point. Like let's say instead of 10,007, put something less, like 10,076 or 10.
Yeah, if I make that number lower, then this whole thing is loaded at 10,000, so it would start trying to execute like here or somewhere.
Yeah.
So it's whatever instruction represents 0, which probably isn't valid, so it'll just crash. So your operating system won't let you execute a legal instruction, so it would probably be an illegal instruction.
Oh, and if you like, let's say the low number is so low that you go up to like 0x05, then you
Yeah.
can execute that.
Yeah, it could be so low that it's not even part of this, in which case it'd be invalid memory. And then it knows to stop, which we'll figure out when we get to virtual memory. All right, so but yeah, good questions. Let's see what C does though, because C is going to do something probably not as good. Okay, so here's C. That's hello world. Everyone agree that that's hello world? That's pretty minimal. Any disagreements with hello world? Looks hello world to me. All right, let's make sure it's compiled. Let's run it. So so it does hello world, and it looks exactly the same as my hello world. It doesn't really do anything different. Any guesses how big this monster is? Few megabytes, all right. Got a few megabytes. Kilobytes. That's 70K, 70 kilobytes for hello world. Did it do anything different than my program? No. See, people think C is like low level and slim and everything. That definitely isn't. That is bloated, right? 70K for hello world? Yikes. Although we'll figure out that C is not that bad. Okay, so before we can explain the difference between those two, so we will explain the difference between the two, let's have another aside. So the beginning of the slide said kernels. So you might have heard Linux kernel before, but you probably don't know what a kernel is. So a kernel is a core part of your operating system. And specifically on every single CPU there is some special privilege mode called kernel mode. And it's a privilege level that gives you access to a whole different set of instructions. So most of the kernel mode instructions are going to let you manipulate hardware directly, and it's going to be more privileged than if you just run some application. So different architectures have a different name for this mode. In RISC-V, it's called S mode for supervisor mode. You might hear it be called kernel mode. On really old CPUs, they had a concept of rings to represent all the instructions. So on like Intel CPUs, it's called ring 0. So they all mean the same thing. It's just a separate CPU mode that gives you access to more instructions that can actually directly manipulate the hardware. The idea behind that is, well, you want a different privilege level so that your application can't just do things that manipulate the hardware without the kernel knowing about it, right? The kernel, in order to maintain security and integrity and make sure everything is independent, well, it needs to have control of the hardware, not you. So the kernel is a core part of your operating system. The definition of the kernel is the software that runs in kernel mode. That's it. So the kernel is the software that runs in kernel mode. It is a separate CPU mode. And these instructions, so like, for example, only the kernel can manage virtual memory for processes. No one else can do that. You have to be in the special CPU mode to access any instructions that have to manipulate the virtual memory. So it kind of looks like this visually. So on some CPUs, there's up to 4 different privilege modes. So in CPU mode U, which is called user mode, that's where your applications and everything execute. So you don't have access to any special instructions. If you try and execute that special instruction, it'll say illegal instruction and kick you out. So S mode is, S mode is the supervisor. So yeah, kernel is part of your operating system that runs in kernel mode. That's literally the definition. So S mode or supervisor mode, that's where your kernel lives. That's the CPU mode your kernel executes in. And below that, that is even more privileged than the kernel itself, is something called hypervisor. The hypervisor, which is in H mode, because your hypervisor would need to maintain virtual machines, so all your operating systems shouldn't be able to interfere with each other. So it manages making those independent so that the kernel can't monkey around with any other kernel running. Yeah.
When you're in kernel mode, can you assign specific parts of your CPU to specific software applications?
Yeah, so when you are in kernel mode, you can do whatever you want. So one of the kernel's job is to schedule processes to run and give them CPU time. So that's that's one of the things your operating system does. Yeah, okay, so yeah, and then below that, which is this M mode or machine mode, is more what you did in your computer organization course. You don't have any applications, you don't care about these privileged modes, you just have access to literally every instruction and you can do whatever you want. So on RISC-V, that's just called machine mode. That's where your bootloader lives and like really low-level things that we won't really get into in this course. Most of this course, we're going to focus on supervisor mode and user mode and the boundary between those two. So, yep.
Kind of confused about the virtual machine part.
Yeah.
So when you say virtual machine, is it like if I take my laptop and I install Windows and Linux? So if Windows is running, it's running on a virtual machine?
Yeah, so how it actually works, so if some of you have set up Lab 0 in Windows, so the suggestion is to use Hyper-V. So Hyper-V, Windows will actually run as a hypervisor. So Windows actually runs as a hypervisor, so it can manage the virtual machines, and then you can install any number of virtual machines on top of it, and it's Windows' job to manage them. Yeah, so that's what it'll do, and it gets kind of iffy because this is virtualization and everything like that is a fairly new concept, so it gets kind of weird.
Oh, is that why you need to reboot it? So like virtualize your current Windows instance so you get different...
Yeah, so this is when you enable it, that's why you have to reboot it, because it has to be a hypervisor now instead of just a regular machine. And we'll get into more details like at the very end of the course. Once we explain how the kernel works, we'll be able to better explain what the hypervisor actually does. So the border between user mode and kernel mode can only be entered by doing system calls, what we did before. So system calls are the only way to get between user mode and kernel mode once an operating system is started. So on Linux, there is only 456 essentially functions you can make to the kernel. That's the maximum number of valid system calls to make. Some of them are like read and write, which we've kind of seen already, open, close, and this is a whole bunch of them. At the end of this course, you'll come back and look at this list and you will understand what each of these are actually supposed to do. Except for init module and delete module, but you did that if you completed Lab 0, and that's how that worked. So the nice thing about having this boundary between your actual applications or user mode processes and the kernel is you can trace all of them. So on Linux, there's this fun little command called strace. So you can type strace before anything, and it will tell you every single system call you make. So we can actually see what our Hello World program does. And we can actually see what C does and compare them, because no matter what language you write it in, your application is going to do system calls. That's the only way it can interact with the hardware is through the kernel. So let's go ahead and we can strace and just run our program. And if we do that, it looks a bit messy. Here, I'll make it bigger too. It looks a bit messy. Well, but it's showing that this is not something we did, but it says write and exit group. So those are the system calls we made. Those are the only ones those are the only system calls we made, and that's kind of what we expect to be there. But we'll see it's kind of jumbled up. There's a weird new line character, so it is also printing hello world as it's showing this. So once you get used to these file descriptors, strace actually outputs everything on file descriptor 2, and we're actually printing to file descriptor 1. So this is from file descriptor 1, this is from file descriptor 2. So if we really want clean output, we could do this. Again, you don't have to know this or be tested on it, but this says take file descriptor 2 and redirect it to somewhere, and then there's this handy file, which is on Linux, it's just called the void, I like to call it. Any bytes you write there just get deleted immediately. So that would delete everything that strace outputs, and I would get hello world. If I want to see what strace is doing, I could delete everything from hello world. So I just delete everything from file descriptor 1. So then I just get without that weird new line break. So I can see when I execute my program, I do a write system call and then an exit group system call. So now that we know kind of how to figure out the ground truth of what things are doing, yeah?
How are languages that are interpreted rather than compiled, how did they do their system calls?
So the question is, if your language is interpreted rather than compiles, how do they do the system call? The interpreter is just going to do the system call for you. So your interpreter is compiled at some point. So it's going to be like your Python interpreter. Python's an executable. The system calls are all done by that Python executable. Yep.
Is the strace with the C file the same? The C
Yeah, the question is the strace for the C the same? So let's see. So we'll strace hello world. And let's just get rid of the hello world part. So if C is minimal, it just needs 2 system calls, right? We just did hello world and 2 system calls. There we go. So that's what C did. So what the hell is C doing? So you can see, we don't know what that means, but that's actually initializing your heap. So that's an operating system call. We have no idea what this means yet. We will. No idea what this means. This kind of looks like we're opening a file called this, which is some cache, whatever. Close, open. We can see that it opened, oh, that looks interesting. So it opened the standard C library. That makes sense, C, standard C library. It should probably load that at some point. So it opened the standard C library with file descriptor 5, and then it read from the standard C library, and guess what? It's an ELF file. That 177, this displays an octal for some reason. I don't know why it's octal. That's 7F. Don't ask me why it's an octal. So it read a bit from the standard C library, did some more stuff, did some more stuff, did some more stuff, did some more stuff, did some more stuff we can't explain yet, did some more stuff we can't explain yet, did some more stuff we can't explain yet. Oh, got an error, inappropriate, very naughty. Did some more things. It initialized the heap again. I don't know, so it had to do it twice. And this is it requested more space for the heap. So it now has a heap. So that makes sense. It had to initialize a heap and read C. So, and then eventually, hey, it did what we expected. It did the exact same thing we did. It said 12 bytes to hello world, exit group. Yep.
So if you were to statically link the binary instead, would it have like a lot less system calls? Because to start, it's like loading the libc library.
Yeah, so the question is if I statically link this, would it have less system calls? And yeah, it wouldn't have to link the standard C library because it's dynamic, and we'll see that next lecture. But yeah, you get rid of some system calls. Yep.
I don't know if it's the same question or not, but if you enable all optimizations, like compile this in release mode,
Yeah.
is there any difference to the?
So the question is, if I compile this with all my optimizations on, will it do any better? And the answer to that is no. So the only thing it will optimize is your main function, and main doesn't do much. It just makes 2 function calls. It might get rid of some C function calls, but won't get rid of system calls. because system calls are the only way it can interact with the operating system. So we can verify that, so no matter what. So let's see, we have Python. I did hello world in Python 3, sorry. So guess what? We can strace it. And let's just get rid of the hello world part and see what Python does. Python does a lot of stuff, but see at the end, it had to do exit group, and there's the hello world. But even between them, it did some things. And before that, you could see that it had to read the file. So it read print hello world, which is the contents of my file. So Python had to load your file. Well, it had to get information from your operating system, it has to make a system call. So to read the file, it has to make a system call. So it read that file twice for some reason. Don't know why it did that. Then you can see most of it is It does a lot of things. Python has some languages. It's going in some libraries, some site customized. So you can really figure out what Python's doing here. See, distutils hack, that's probably an intern did that. See, look at all the stuff Python's doing. So if we don't want to scroll through all this, I generated it earlier. So this will see how many lines there are, which is like how many system calls it makes. So Python made about over 350 system calls to print hello world. Well, to reg on something else, let's say JavaScript. Hello world, so we can strace JavaScript too. Oops. Oh, 1, sorry. Wow, that scrolled a long time. So JavaScript, what does JavaScript do? Well, at the end, it did exit group. Before then, it started closing some files. Where's hello world? It's doing, who knows what the hell JavaScript is doing? That's bad, you can't even find the hello world system call. Oh, I passed it? Wait, it's somewhere in here? All right, well, whatever. It's somewhere there. And I generated it earlier, so we can see how many system calls JavaScript makes, and over 1,000. So yeah, common JavaScript W, right? Yeah, you can tell I don't really like JavaScript, but I have numbers to back me up. So the beginning system calls, it looked like it was finding the standard library. Then it loaded the standard library in C, and then eventually it set up the heap and then did hello world as we expect it to do. So what you can think of the kernel is, it's kind of like a long-running program, but it's just running in a different CPU privilege mode. And writing kernel code, because it's a long-running process, it's more like writing library code, like there's no main or anything. So if you've done lab 0, you're actually writing kernel code, and you're requesting it to be loaded by the kernel and executed by the kernel. So your code will actually run in kernel mode. So that's what you do. You create a module for it. And in general, kernel code's loaded on demand because a lot of it is device drivers and things like that. So the kernel will know what hardware gets plugged in and what code that corresponds to, and try and load and execute the appropriate code. So when you're doing lab 0 and you're writing a kernel module, you can execute privileged instructions. You can do whatever you want there. So right now, it's just printing some messages to the kernel log because the kernel doesn't have printf. It doesn't have a standard C library or anything like that because it's running in kernel mode, so it doesn't have anything. It needs to enable you to have those things. So if you really wanted to and you knew what you were doing in your code for lab 0, one of the things you can do is kill every process. Just kill every process. And whatever's running, you can just kill it if you want. Like, there's you could read any process's memory. You can do whatever you want because your code is running in kernel mode. It's supposed to be, high quality code, which is why a bunch of people would review it for the actual kernel. But since you're writing your own, you can just do whatever you want. So there's different kernel architectures, which we will not have time to go into. So instead of that, I will just let you go and say, I'm just pulling for you. We're all in this together.